Welcome to our seminar on 400G CEI 4.0 characterization and compliance testing. Time to get serious. This is our agenda of what we're going to cover today. I'm going to just do an introduction on where we are with the standards, and then I'll turn it over to my colleague Rob Slay, who will talk about output testing, transmitter testing. He'll turn it back over to me to cover the receiver side, and we'll have a summary and wrap up with some time for Q&A at the end. Let's start by talking about the state of the 400G class standards. And by 400G, I always refer to that as it's not just Ethernet, it's a whole class of standards, and you can think of them as all the data center standards that use 40 gigabits per lane as the lane rate. 802.3, it was originally the BS project, but now the BS project is done, it's released, and that's where the groundwork was really done for 400G. It covered a series of optical reaches, all implemented with single-mode fiber, and the electrical chip-to-chip and chip-to-module interfaces. And they're based on PAM4 modulation. Most of them are at 26.6 gigabaud. One of the optical standards uses twice that rate at 53.1. The Optical Internetworking Forum did a series of electrical standards called Common Electrical Interface 56G. These cover 5 different reaches. They're based on multiple modulation techniques, although the principal ones are done on PAM4, and they cover a range of data rates running up to 29 gigabaud. These were released and published in December last year, and they're released as CEI 4.0. IEEE is also finishing a project to pick up the multimode fiber. This doesn't have the 400G, and it has 250, 100, 200G with multimode using PAM4 at 26.6 gigabaud. They're trying to finish this up. It's been in that state for over 6 months now. There's some issues with the TDEC-Q measurement, getting repeatability, and those are very close to being resolved. Fiber channel is another optical and electrical standard. It's used in the data centers, and it has short and medium reach implementations with both multimode and single mode. It runs a bit faster than Ethernet, 9% faster at 28.9 gigabaud. And it's in the same status. The standards work is all done on this, the technical work, and they're waiting to see what happens with the TDEC-Q measurement, because TDEC-Q is used in fiber channel, and if there are any changes in Ethernet's definition, then the parameter tables might have to change in the fiber channel. Second generation 400G projects are getting started. You noticed I said with the CD project there wasn't a 400G. That was because technology really wasn't available to implement that in the time they wanted to finish the standard. So now they've started a project 802.3 CM, which will add the 400G and multimode fiber. And the CN project, in the original 802.3 BS, the long reach, which handles the typically 40 or beyond kilometers, was not done. So there was a project started, again, for the same reasons. The technology was not in place to implement it at the time, but now the technology has matured a bit, so that project is starting next month as well. Consortium for Onboard Optics, this is a closed standard. They have released their version 1.0 based on the electrical 5 from OIF and the optical 5 from 802.3 BS. So that work is pretty much reused. So important note I want to say on all these standards that are not released is that they're very dynamic, and it's very important that you're using the latest draft version, because there are some significant changes that have implications not only in the test limits, but in some cases in the test methodology. So just be sure you're using the latest version. Okay, so where are we with turning on these links right now? Well, a year ago we were turning on the individual components. We were turning on some of the switch chips. The SerDes were certainly done, and the early modules. And now people are putting entire systems together. They're laying out switch cards, and all the ecosystems are in. So we're putting all that together. And as we start testing some of the complete links, we're finding some surprises that, one of the reasons that some of these standards are dragging on is because of real testing with real silicon has uncovered these surprises and required some changes. and not only in the parameter value tables, but in some cases the actual method of how we do the testing. So that's kind of where we are, and with that, I will turn it over to my colleague Rob to talk about transmit.
Well, thanks very much, Steve. So I'm going to cover some transmitter test measurements that are both optical and electrical in nature. But I'll start out by just talking about some patterns that are being used for PAM4 testing. Wanted to make you aware of JP03A and B. JP stands for jitter pattern, 0 level to 3 level. And these patterns, while they were initially being proposed in 802.3 BS, they are no longer used in BS or CD. Wanted you to be aware of them, but they're not part of these standards that are being worked on today. Instead, PRBS 13Q is a repetitive 8191 symbol PAM4 sequence, and that's being used for the victim channel for all of the transmitter tests. PRBS 31Q is the sort of the workhorse pattern for the victim channel and receiver tests, and then it's also the pattern that is being used for the aggressors in both transmitter and receiver tests, so the adjacent lanes. And then SSPRQ stands for short stress pattern, random, quaternary, and it's a 2 to the 16 minus 1 PAM sequence that's comprised of 4 sequences that have been pulled out of the PRBS 31 pattern. So it's a very stressful pattern, but it's short enough to be analyzed using today's test and measurement tools. And so this is the workhorse for the optical transmitter test measurements. Talking about optical, let's have a look at NRZ versus PAM4. For NRZ testing, you might be familiar with the optical modulation amplitude measurement, or the extinction ratio, and the IMASC was a definite workhorse when it came to transmitter test. And there's, you can see the eye diagram, put up an IMASC to determine pass or fail criteria. One of the new things that have been coming along for 25 and 50 gig lanes is a new measurement called transmitter dispersion and eye closure, or TDEC, and it replaces the legacy transmitter dispersion penalty, or TDP measurement. Because the links themselves on PAM4 run at relatively high symbol error rates, the use of FEC is required to correct for that, and that creates a number of new challenges. Outer OMA and outer extinction ratio are new measurements for PAM4, and note that there's no IMASC test anymore. And TDEC-Q is essentially replacing the IMASC and TDP. And I also wanted to make you aware of a new measurement, relatively new, that's been added to 802.3 CD, and that's transition time. TDEC-Q stands for transmitter dispersion and eye closure, and quaternary it's the PAM4 version, and it tells you the performance of your transmitter relative to an ideal transmitter. Looking back at NRZ TDP measurements, it was really a BER measurement using a BERT. You'd set up a golden transmitter, and you compare the performance of your device versus the golden transmitter. The measurement itself would determine how much additional power was required at the receiver to compensate for the non-ideal performance of your transmitter. For TDEC-Q and PAM4 measurements in 400G applications, we indirectly measure the symbol error rate using an oscilloscope, so no BERT is required. It's a very cost-effective and fast measurement. How do we go about doing this? Well, this is the description from 802.3 BS. So you start with that short stress pattern, SSPRQ, which is 2 to the 16 minus 1 symbols in length. And you run that through a test fiber. And this is specific to 802.3 BS. You don't use this fiber for 802.3 CD. And you characterize the oscilloscope noise, and that gets backed out of the measurement. So that would be done during a module calibration, for example. It's done automatically. And then you apply a virtual 5-tap T-spaced FFE to optimize the eye opening in order to minimize the TDEC-Q penalty. So on that PAM4 eye diagram, there's 2 histograms that are applied, and it's very specific. It's called out in the standard. And essentially what we do is take the samples and compute an effective power penalty in dB. And this is your TDEC-Q result. So the smaller the number, the better or more ideal your transmitter is. So TDEC-Q has definitely evolved over time from the beginnings of 802.3 BS probably a couple of years ago now to where it is today with 802.3CD. And I won't go through all of these, but the key ones that I wanted to point out were related to 802.3CD. And one of them is the fact that the decision thresholds are now allowed to vary from ideal, so up to 1% of OMA. So this is a slicing threshold that's allowed to move up and down. And then, as Steve mentioned, there's also additional work that's taking place that would have some additional changes to the TDEQ algorithm in 802.3CD as well. So those should be finalized, if not at the next meeting, then the one after that. So the one thing I wanted to point out here is that there's been a lot of work going on within the committee meetings to optimize the TDEQ measurement. Where it's ended up is the fact that the TDEQ measurement is now much more representative of what's going on inside a real system or a real receiver. And you'll see in a moment that it's paid dividends. So when you're making TDEQ measurements, it requires a very accurate optical reference receiver and a very robust clock recovery design, whether it's in software or hardware. So imagine what's going in after going through a test fiber. What's going into your optical receiver is a very degraded eye. It's incumbent upon your clock recovery unit, or CRU, to recover a clock to trigger the oscilloscope. In the case of a sampling oscilloscope, such as the DCAM shown here, we have a new N1078A that's capable of locking onto optical signals, whether they're running at 26 or 53 or anywhere in between, all the way up to 64 gigabaud. The oscilloscope itself has to apply an ideal reference receiver. So this is a fourth-order Bessel-Thompson with specific 3 dB bandwidth and roll-off. And then we also apply a TDEQ equalizer, and that will open up the eye and allow us to measure TDEQ on that equalized eye. So you can see that the signals that we're dealing with can be quite degraded. In fact, the signals in the bottom left-hand corner there, those are actual signals that we use in production to test our clock recovery. So we can recover a clock from a totally closed eye. Some measurement tips for characterizing TDEQ. You want to use a measurement solution that's very fast, flexible, and accurate. A compliant TDEQ measurement requires histogram optimization. So those are those two slices. They're allowed to move to the left and right slightly. There's also that threshold optimization of the slicing levels. Those can move up and down. And our recommendation at Keysight is to keep those enabled at all times. You have the ability in the software to turn them on and off, but because they have minimal impact on throughput, we recommend that you keep them on because it can have a significant impact on the accuracy of your result. On the other hand, 802.3CD also specifies an iterative optimization technique. And again, you can turn this on or off. And what we found is that it typically results in only a couple of dB difference in TDEQ. So if you have the margin, we recommend turning this off because it can increase your test time by 2 or 3x. Something else that you can do is apply a seed equalization or seed taps for the TDEQ equalization process. So you run through the entire process once, you get valid tap settings, you use those to characterize future devices. One other thing that you can do is make sure that you have a very powerful CPU when making these TDEQ measurements. They're very intensive in terms of the computations, and so the more cores that you have, the faster the measurements. And so as an example, if you're using a powerful CPU, you can get your TDEQ test time on 4 channels down to less than 15 seconds for all 4 channels, as opposed to a minute or more if you're using a less powerful computer. So is TDEQ, is it working as designed? And an example is, consider a typical PAM4 receiver, and you have 2 transmitters, A and B. If transmitter A has TDEQ of 2 dB and transmitter B has 3.2 dB, should you be able to make any predictions about the power levels required at the receiver to achieve a specific SER, or symbol error rate, with each transmitter? And there's been a lot of work that's taken place there These are some of the latest results from a paper that was presented at 802.3 CD in one of the meetings there, and we received permission from the author to share that. And what it shows is that there is a definite linear relationship between TDAQ and receive sensitivity. And it's only through this optimization process of the TDAQ algorithm and model that we are now starting to see very good correlation between TDAQ measurement and real transceivers and the performance there. So what should you watch out for as the signal level is lowered? Are you getting unexpected results? Well, signal attenuation should not alter that TDAQ value. So remember, we talked about characterizing oscilloscope noise because it's mathematically removed from the calculation. So you have to ask, well, can I just use any scope, or are there practical limits to this process of removing the noise? In addition, as TDAQ errors occur with very small signals, do we expect that those errors are going to increase the TDAQ or decrease the TDAQ? And have you observed any TDAQ measurement changes as a result of your OMA getting smaller? So we certainly have. Here's a couple of examples where as OMA got smaller, on the left-hand side, our TDAQ got very small and actually started to go negative. And on the right-hand side, our TDAQ actually got quite a bit bigger as our OMA got smaller. So why might that be? Well, in the case of high-noise receivers, it can definitely impact TDAQ accuracy. So because high-bandwidth receivers will have more noise, and very often these are unamplified wide-bandwidth receivers, it will have an impact when measuring low-level signals. So our recommendation here is to use an amplified receiver if possible, or a receiver with very good sensitivity. And don't forget to perform that module calibration, because that allows the instrument to then back out that intrinsic noise from the measurement itself. Likewise, if you're dealing with very degraded signals or closed-eye signals, what can happen is that those degraded symbols get misinterpreted to a nearby level. So the software thinks that that sample belongs to a particular level when in fact it's not. So it's making a mistake. And these misinterpreted samples can lead to a better TDAQ result than expected, and that should not be the case. You shouldn't see that behavior. So when you're characterizing your TDAQ solution, make sure you look for that. And our recommendation is to use thoroughly tested TDAQ algorithms, such as the TDAQ algorithm in FlexDCA Rev 5.8 or later. As I mentioned, there's new transmitter transition time for optical PAM4. I just wanted to make sure that you were aware of that, and that it could be measured on the square wave or on a very specific region sequence for an SSPRQ pattern. So rise time, string of zeros to threes, and then fall time, a string of 5 threes to the 6-0 combination. So looking at some key electrical measurements, as an example at TP0A for 802.3BS, there's level separation mismatch ratio or linearity, there's SNDR, and several key measurements around output jitter, JRMS, J3U, J4U, and even an odd jitter. And you can see that those measurements are made at the end of a test fixture, TP0A. You can't reliably measure at TP0, so the standard allows for a certain amount of loss and reflections, and the measurements actually made at TP0A. So you might think that you recognize some of these J3, J4, even an odd jitter from past standards, and so they should be pretty straightforward to measure, when in fact these new measurements are performed very differently. The legacy even an odd jitter, J5, J9, they were made on all edges of an NRZ pattern. These new measurements are made on 12 specific edges of a PAM4 of a PRBS 13Q pattern. Not only for 802.3BS and CD, but they're now part of CEI 56G, MR, and LR, medium reach and long reach. So don't just pull out your oscilloscope and press the JN button or the EOJ button, because chances are it hasn't been optimized for PAM4. So why did the standards make this change? Well, different transmit architectures are used to generate PAM4 signals. There are some designs that use different clock buffers to generate the MSB and LSB. So you have two NRZs coming together that can get combined. If the uncorrelated jitter on each of those sources is different, then you can have different jitter depending on the edge that you're looking at. If you're only looking at the clock pattern, the JP03 pattern, which was the original method, then standards recognize that, hey, we could miss some potential issues here. We need to change our approach, hence the 12-edge jitter measurement. So this is where we measure RJ, PJ, and a histogram on 12 specific edges. We combine all of those edges and report a result. For EOJ, we use that same PRBS 13Q, but we report the maximum EOJ from each one of those 12 edges. Key site oscilloscopes, whether it's the sampling scope, the DCA, or our real-time scopes, we have this measurement now available for you. And if you're using Flex DCA, we actually report all of the results from all 12 edges, so it's a very handy troubleshooting tool. So there's some measurements at TP1A. So in this particular example, this is a chip-to-module or a CTM compliance measurement. Inside the transmitter, you expect to have a clean eye, but at the test point at TP1A, because of the fact that there can be up to 12.2 dB of loss, you expect a very degraded eye. It might not be that bad, as shown here, but will definitely be closed or very close to closed. So we need to be able to recover a clock from that, apply a continuous time linear equalizer, or CTLE, and then using either a real-time oscilloscope or the equivalent time oscilloscope, equalize that signal and start making measurements on that. And here's another example of, these are actual screen captures of test signals that we use in our production facility to test our electrical clock recovery. So you can see that we're able to deal with entirely closed eyes here as well. So with that, I'm going to turn things back over to Steve.
We're going to focus the rest of the session talking about the Ethernet chip-to-module interface of all the different clauses that we could be doing a deep dive into. This one, I think we see the most questions coming out. So I'm going to start talking about just a general thing that we're running into quite a bit with people starting to work with PAM4 in the lab. Just as Rob was talking about how you need to be careful with those jitter measurements because the definition has changed. Well, one of the things we're finding is how you do the basic receiver test really has to change when we're dealing with PAM4. Okay, so the bit error ratio tester is still the primary tool we use, but we're going to configure it a bit different in the test setup, and I'll show you why. So let's first show the original test setup, and this will show why the changes occurred. So we have a device under test, and we're trying to test the receiver, which really says we're trying to determine its ability to handle signals that have some amount of impairment in them. And the way we do that is, again, with a BERT, and the BERT has a pattern generator which generates carefully calibrated amounts of impairments. And with the output of the pattern generator, we put that into the receiver either directly, or in some cases we put it through an external channel, which is usually a piece of circuit board trace, and that goes into the receiver under test. Now, the issue is where do we get that information that the receiver is receiving this impaired signal correctly or not? Well, it's inside the device under test. So somehow we have to get access to that signal right there at the output of the receiver to determine how good of a job it is in recovering the signal. And the way we used to do that, or the way we traditionally did that with a BERT, is with loopback. So we take that signal out and we loop it through either internally or externally to a transmitter that is in the device under test, and we retransmit that signal through a very short piece of cable because we don't want any corruption in that loopback path, and we put that into the other half of the BERT, which is the error detector. So this is the way we've been doing, using BERTs for, at least 30 years, and everything was fine until we got to PAM4. And the reason is that loopback path has to be clean. As I said, it's a short cable, and any, corruption in that can introduce errors at the input of the error detector. And if we have errors occurring at the input of the error detector, then those will be added to the errors that we're trying to measure from the receiver of the device under test. So it's really important that we keep that loopback path very clean. And the problem is now with PAM4 links, these are not designed to run error-free. They used to run error-free, and all the way through 100G, our links were running better than 1E-12, and now we have targets of 1E6, 1E5. They typically run a little bit better than that, but still, they're not error-free. So we can have the potential for adding errors at that input of the error detector. Now, what just happened there is I'm showing that loopback path is more than just that short cable. It really encompasses the loopback path within the DUT itself and the transmitter in the device under test. A lot of the problems are on the transmitter side. You can have nonlinearities, you can have I-skew, you can have bad signal-noise ratio, and all of these problems, even with high-performance equalization in front of the error detector, which we have, you really can't cover problems with skew and linearity, really bad linearity, or impaired signal-noise ratio. The problem is that, is your loopback path error-free enough that you can make a repeatable measurement? And, this is the basic problem. And the real solution is just to get rid of the loopback path and the error detector altogether and use an error checker in the device under test. Now, the standards are pretty much implying, or in some cases actually mandating, that host chips have error detectors in them. They don't put that requirement in for modules because modules are limited with power and size, but we're finding that most of the modules have that internal error checker. So if you have that error checker available, you should definitely be using it to avoid this confounding problem of adding errors in front of the error detector of the BERT. So that's the big change that's happened from testing in the previous NRZ to PAM4 with links that don't run error-free. So now let's dive into the specifics of this is actually Annex 120E, which was the 200G, 400G attachment user interface for 802.3bs. And like all of these attachment user interfaces, they use a set of compliance boards or a host compliance board, which emulates the module for testing a host device, and a module compliance board, which emulates the host. Now, you see that the module compliance board is a bit more complicated because you need power supplies, and usually you have an interface, a management interface bus on a module that you have to bring out to control it. So that's what the extra connectors are on that board. Regardless of your testing, if you're only testing hosts or you're only testing modules, you actually need both boards because you need the opposite board for the purposes of calibration when we do the test setup. Both boards are tested, are specified for return loss and insertion loss as a mated pair. Now, some of the standards give a suggestion of how much allocation is given to the module board versus the host board for the through loss, but that's not always the case in all of them. But they are verified as a mated pair. The first thing you want to do when you get a new set of compliance boards is verify them, even though they might give you a piece of paper in them that say that they've been tested, and they might even give you the S-parameter plots to show you what's going on. It's best if you do this yourself. I've had more than one user that's reported that they've lost an awful lot of time in their lab doing a whole series of tests with their DUTs and having some repeatability problems and finding out that their compliance boards actually are not meeting the through or return loss characteristics. Okay, and one of Rob's slides, he was showing the TP1 and TP1A, and these are the designators that they use quite a bit in the standard. And in the beginning, they have this table, regardless of what InfiniBand or OIF or Ethernet, you see the same illustration in all of them. And until you have this memorized, you might want to photocopy this page and just have it up on your desk because it just refers to where you are. So when you're doing the input tests, where do you put the signal and where do you do the calibration? And the same thing for the output tests. So I'm going to talk about the chip to module, and there's two different tests depending on whether you're doing a host or a module. They're very, very similar. The module is a bit more complicated, so let's start with a host. All the tests are done with a series of static stresses. So as opposed to doing a jitter-tolerant sweep, we actually are going to do 5 discrete pairs of amplitude and sinusoidal jitter frequency, and those are we're putting in. So there's no interference used or noise used in the chip-to-module test. It's a classical stress recipe, so the sinusoidal jitter is primarily to test the PLL tracking. It's at relatively low frequencies, and then the high-frequency components are through random jitter and bounded uncorrelated jitter, which are added. So the 5 frequencies that define the 5 different tests that you're going to do are shown in the table here. You see at the low frequencies, they're very high, 5-unit intervals of jitter, which is where the PLL should be tracking, all the way up to 40 gigahertz, where we back it down to 50 milli-UI, because this is beyond the tracking range of the PLL. And then the RJ and the budge are added to the stress mix through the whole fixture. I'll show you the calibration setup in the next slide. And they're initially set to the maximum values that the transmitter is allowed to put out. So in the case of a host, this would be the maximum values that you can get from a module, which in the IEEE specification at 1E-5 is 200 milli-UIs of I width and 30 millivolts of I height. That's the worst case. Per the IEEE definition, those are the worst case of any of the 3 I's that you see in the waveform or in the eye. So de-emphasis is applied at the transmit side to get the best eye opening, and then there's a CTLE in the reference receiver, and you select from the optimum CTE value. So reference receiver is used for the stress calibration, and crosstalk has to be applied in the counter-propagating direction. Now, if you're testing a host device, the crosstalk is generated within the device itself, because you're testing the receiver so the device can generate its own transmit signal to do its own crosstalk. But we need to calibrate it with it, and we'll show that as well. So the aggressors, for calibration purposes, it's a PRBS 31Q signal. It's at the same symbol rate, but it has to be asynchronous to the test signal, and that's to assure that you get a phase slip, make sure that if there is any problem with eye closure coming about because of a coupled edge through the crosstalk, that at some time that's going to pass through where the slicer is in your receiver, and so if you have a problem, it's going to show up. So here's the test setup that, again, this is from the document. So this drawing's been used in one form or another for decades now, and it shows that it's aged. But the only thing that's really been updated in is reference receiver, and we've added the CTLE to it. Now, when you look at this, one of the first things you might notice, and the first time I was using this, I had scratched my head because I was confused on this, is I see this crosstalk generator in there in a calibration mode, but you look at where that signal goes in, that whole module compliance board is only used for calibration. So you're going to unplug that board, and with the crosstalk generator where it's shown, it's going to disappear when we do the test. Well, again, that's because the host itself is going to generate its own crosstalk. And the only reason we put that in calibration is we want to compensate for any coupling, any crosstalk that's on the compliance boards themselves. And they typically will have some effect there. You'll see a little bit of eye closure, and you don't want to overstress the DUTs. So for the purposes of calibration, we want to have that crosstalk in there when we do the calibration. As I said, it's generated by the host itself, and it's inherently asynchronous to the data. So the BERT is the pattern generator, and the air counting is performed by the host. BERT is only being used as a pattern generator. We're not using the air detector in it. See the drawing with the rather complicated setup for the stress generation going into a pattern generator. This is a 30-year-old drawing, and back then, BERTs didn't have jitter generators built into them. They had a modulator input, so these would actually be all signal generators on the outside, but now any BERT that you buy that can run at this speed, regardless of who the vendor is going to have all these stressors built into it. So that really is, even though it's a complicated drawing, it's really a single box that you use. The test pattern is a PRBS 31Q. Modules are assumed to be transparent to FEC, so even though we're using FEC in the real links, the modules don't process the FEC. So for the purposes of testing, we don't have any FEC in there. So the standard says you can use either PRBS 31Q or scrambled idle, but if you're using a BERT, PRBS 31Q is going to be your only option because the scrambled idle pattern is too complex to generate within the BERT. Again, because FEC is not being processed here, this is a Burr measurement. It's not a FEC-SIR measurement as in the chip-to-chip spec. It is just a simple bit error rate, and the test limit is better than 1E-5. So that's how we do the host test. Now let's shift gears and talk about the module. So you see it's a very similar test setup, which is a couple of changes. The key one is that in one part of the testing, we add more channel length in this, and we add an external, what they call a frequency-dependent attenuator, which is really an ISI trace on a circuit board to get that up. And actually, depending on the standard, whether it's OIF or IEEE, in some cases you have to run two sets of tests. You run one without that. They talk about the short channel and the long channel, low loss case and high loss case. And so you run all 5 tests with the 5 different jitters without the ISI trace in there, and then you add the ISI trace and repeat the testing. It's the same 5 stress frequencies and amplitudes, so they don't change. It's the same setup you use for a host, but the calibration targets are a little bit different. They assume that the equalizers are not as powerful in a module, so the requirements for the jitter coming out of a host transmitter are more stringent than they are for a module. So now we have 22 milliUIs is the requirement, and 32 millivolts is the I height. Crosstalk generator, again, is used for calibration purposes, but removed when we do the actual test. Now, unlike a host, the module can't generate its own crosstalk, because where's the crosstalk going to come? Remember, we're testing the electrical transmit input on that module. That's the test we're performing right now. So the crosstalk is in the receive side, because they say it's in the counter opposing direction, which means you have to stress the module for the purposes of putting an aggressor in on the receive side. That is an optical signal, okay? You know, an easy way to get that, an inexpensive way to get that is just use a second module. So get a second dot. First, validate that it's compliant, its transmitter is compliant, because it has to be a compliant transmitter. So run through all the tests that Rob was just talking about. You validate the optical TX output, and you feed that into the optical receive side of the module, and that's where you get your crosstalk signal. Again, that has to be asynchronously sourced. Now, some modules even have the prescribed test pattern. It's a PRBS31Q. They have a test pattern generator built right into them, in which case all you have to do is supply them with a clock. But that clock cannot be derived from the BERT clock, because it has to be an asynchronous clock. And then you need to measure the burr. Now, again, if you have an air checker in the module, and I'm finding most of these 400G class modules do have air checkers built into them, so hopefully you do have an air checker built in and use it, because if you have to use the optical link, the optical burr is even worse than the electrical burr you're trying to test. You know, the test limit's 2.4 E minus 4, so it's half of an order of magnitude worse than the link we're trying to test, and that could get you into real trouble. But if you do have to use that mode, then you should use an optical grade O to E, not a second module. In the past, you used to use your own module as the optical receiver, get the electrical signal to feed the ED on the BERT. But again, you know, the modules aren't that good, because these links aren't designed to run error-free. So you should use an instrument grade O to D, which will give you higher bandwidth and a lower noise floor. So it'll help you a little bit, but still not guaranteed. Anytime you're not using that internal air counter, there is a possibility that your reading is actually going to be worse than real life. You're overstating the burr because you're adding additional errors at the input of the air detector. And the test limit is the same. It's 1 E minus 5 that we had for the host. Let's talk a little bit about stress calibration, because we're finding that stress calibration is very difficult to do for this chip-to-module standard. It's particularly difficult in the case of the module test when we have the high-loss channel, or when the added board is in, as Rob mentioned. Depending on the standard, again, it's either 12.2 or 13.4 dB that is the total loss in that channel, and that's quite a bit of eye closure. The way the standard works is you initially set those values of RJ and budge up to the worst case of the transmitter, as I said, and then you use the RJ as a vernier control. You tune that in the BERT to adjust the amount of eye width. So that's how you tune it to make up for the noise in the system. But there's additional tuning allowed in these setups as well, which makes things really complicated. The first thing is, in the reference receiver, there's a series of predefined CTLEs that each one has a different gain, and depending on the standard, most of these are half dB steps now. So there's either 9 or 13, a choice of 13 that are available that you use, and you pick the one that gives you the best eye opening. Now, the standard tells you the definition of best eye opening is the product of eye width times eye height. You multiply those two numbers together, and you pick the CTLE that gives you the best product. We have found that that is not always the best case. Quite often, we're forced to do this. We start with that value, but then we end up settling on one that's one step away, which is half a dB, and it's usually in the lower direction. What happens is when you have too much CTLE gain, you actually start sacrificing some eye height, which is kind of counterintuitive. You would assume that adding more gain is going to give you more eye height, but what you're actually doing is you're overloading the system, and the previous symbol is overshooting, and when it comes down from its overshoot, it's dipping into the eye that we're measuring, and so you're actually seeing some eye closure from that overshoot effect. So again, start with the best, but if you can't get there with the best EWEH product, then try moving one side either and see if that makes things better. And usually it's in the lower dB that does it better. Then we're allowed to put a feed-forward equalizer on the transmit side, because in real life you do have a feed-forward equalizer, and the standard says pick the best tap settings on that to give you the best eye opening. Now, in the test setup, you're not using a DUT as a transmitter, you're using a pattern generator and the BERT, so this is being done with de-emphasis in the pattern generator, and it's the standard de-emphasis setup, which is a 4-tap de-emphasis with a cursor in position 2, and pick the value that gives you the best setting. Now, this can be a very slow process if you're measuring this, eye height, eye width product every time and changing these values, because you have a lot of knobs to turn. And you can end up spending, I talked to one user that actually literally spent a day and a half with one particular test setup to find the values that gave him the optimum setup. So I'm going to show you a shortcut on the next slide that will speed that up considerably. Now, what we're finding with this stress calibration is that the eye height is not generally the problem. There's not a lot of margin to spare, but it's the eye width that we run into trouble. The vernier control on it is the amplitude control of the pattern generator. And since the pattern generator can put out, more than 2 volts, it's not the problem. But you do have to be careful at one point in the standard. You cannot exceed the 900 millivolts, the maximum transmit output, in the non-de-emphasized portion of the pattern. So you find a part of the pattern, and you don't do this in eye mode, you do this in waveform mode. You find, actually you ask the scope to do the amplitude measurement for you, and it does the same thing. But essentially what it's doing is it's going to look through, and with the histograms, it's going to find the non-de-emphasized portion, which you have consecutive symbols of the same value, and that cannot exceed 900 millivolts. So here's the trick to speed up that process of figuring out what tap values you need for the BERT, for the de-emphasis. And the way we do this is with a DCA. So here we have, on the left side, you see our reference receiver. We have our Bessel-Thompson filter, followed by that CTLE. And as we said, that's the table of selected values. Those are already built into the DCA for you, so we've already done the work. You don't have to load the coefficients manually. And then what I did is I added the feed-forward equalizer on the receive side, okay? Now, it's a linear system, so since it's a linear system, I can put that equalizer anywhere. In theory, I can put it on the receive side or the transmit side and have the same effect. In actual life, even though it is a linear system, there is a little bit of differences because of where the noise is in the system. When you put the FFE on the receive side, you're going to be working on the noise that's in the channel as well, whereas on a transmitter, it doesn't have that noise. But in any case, we put it here on the receive side just for the purposes of calibration, and I take the signal out of that, and I click on the box, which you see on the right, the menu that's opened, for the equalizer, and I set it up to the value that, again, the 4 taps is what is prescribed by the standard, and the precursor's in position 2, and I click that little box right underneath taps that says automatic taps. You see that little box that's checked, and the software and the DCA will do all the work for me. It goes through and it finds the optimum set of tap values, and I load those into the BERT, and now when I make the measurement, be sure that you're making the measurement. You're not, putting two feed-forward equalizers in it. So you move your measurement point to the point out of the CTLE before the FFE. You only use the FFE to determine what values to load into the BERT to get the optimum value. So you can take those values, and instead of spending a day and a half, you can do this in just a few seconds. Now, the one thing I will say is use these as starting points. Quite often, you still are not going to get the prescribed eye width when you're doing this. You have too much noise in the system, and that's because, again, we're putting the FFE for this purpose in the receiver to determine those tap values, and it's working on the noise in the system, which is a little bit different than what happens when we move it back to the transmitters. So you start with those starting values, and then you can try just fine-tuning those a little bit to get the eye widths where they need to be. Even when you do all of this, you might still run into problems with the calibration. And we've had a lot of problems in the lab with this, and I work with quite a few of our users, in doing support calls on this very same problem. And what happens is, I turn that RJ all the way down to 0, and my eye is still too closed. And so what's going on in this? And if we test with that, you're overstressing the duds. So it's not a valid test. You're making life a lot harder for yourself than it needs to be. So the first thing to check is look at your compliance boards and make sure that they're meeting the requirements called out by the standard. It's not just the compliance boards, it's the entire test setup. So you've got that channel in there, you've got all the cables. You need to make sure that that's compliant, not only in the through, but particularly the return loss. And return loss is where you're likely to get into trouble because reflections are deadly in a PAM4 system. And so if you've got bad return loss, you might have reflections that are causing trouble. Now, if you suspect that's the case, the sure way to verify that is take everything apart, move over to the VNA, de-embed your cables on the VNA, put it in your test setup, and verify the return loss of your system. But here's a quick and easy way. Actually, I came up with this when we were having this very same problem in the lab, and it's a really clever way to save you the time of having to rip everything in your test setup apart and move it over to the VNA. So while you have that set up where you're trying to find the optimum tap values that I showed on the previous slide, remember I set that to 4 taps because that's the prescribed equalizer setup in the standard. So just take that number and set it up to a really high value. In this case, I'm showing 12, put 20, 30 in there, and see what happens to your eye width. If your eye width suddenly gets a lot better when I put a large number of taps in the feed-forward equalizer, let's think about what's going on. Those long tap values, that's a time constant so slow, we are not compensating for frequency-dependent loss in the channel anymore. What we're really compensating for is we're doing reflection cancellation, right? So if that makes the problem better by selecting a high number of taps, then it's quite likely that I have a reflection problem in my test setup. So in this case, actually, that's not what's going on because you can see all of those far out taps are all valued at 0. I just did that to grab a screenshot. But when we did this in our initial test in the lab, that's exactly what was going on. And we were able to troubleshoot the problem without having to go to the VNA to figure out what's going on. So, and as I said earlier, that the amplitude is generally not a problem, but again, it's a trade-off. This is where you're playing with your CTLE settings and your de-emphasis settings. You can play with all those to see what give you the best values. In this case, we're not even there. This is a typical example, and we're still not quite meeting it because our target, again, is 22 milliui, and you see we're a little bit of trouble with our eye width. Well, actually, we're passing. We're just passing in this. You can see that we just have enough margin with this particular setup. Our 22 milliui is the target, and we have 230 milliui in this case. And it's always the upper and lower eye that have the trouble. The middle one usually has plenty of width and height, and again, that gets into the tuning of the CTLE that they prescribe in the standard. And that really kind of concludes our seminar today, so I'll just go through a bit of a summary, and then we'll open it up for Q&A. First thing I want to say is a reminder that the standards are still moving until they're actually published. You be sure that you're using the most recent draft when you do your testing. On the transmit side, there are many new measurements that were done. As Rob was saying, don't use the jitters that are already built in your instrument from NRZ because those definitions have changed. There's been a lot of work going on with TDEC-Q, and You need to use a very low noise reference when we're making those TDEQ measurements. When we're moving over to the receive side, you should use the internal air detector if you have it available, because the links don't run air-free anymore. Otherwise, you don't get accurate and repeatable results. And these standards have very, very little margin. It makes it very difficult to do the stress calibration. So make sure your test setup is very clean and validate your calibration before you're doing your testing. Okay, and with that, we'll open it up for Q&A.